So we want to design a 4-bit adder subtractor circuit. This is the diagram of an adder IC, 4-bit adder. So this is 74LS83, that's the chip number, and these are the sort of pin diagram. I haven't not pin diagram, just the block diagram I would say. So I haven't identified the pin, but these are the important inputs. So inputs and outputs. So there's a one 4-bit here. I will show with a different color. So 4 bits here, one of the 4 bits, and this is the other 4-bit. So these two 4 bits are added in the circuit, in the IC, in the chip, and this is the 4-bit output. There is a carry in, which is this one, and there is a carry out. These two pins, carry in and carry out. Now we want to use this chip as a 4-bit adder subtractor, 4-bit adder subtractor, but when we want to add, it's very simple. We just we just feed in the bits here, the input bits. So both the bits here, 4-bit here, one of the 4 bits here, and the other number here. Both are 4-bit numbers, binary numbers of course. But when we want to subtract, we have to use some other circuitry, and before we do that, we should recognize one of the usefulness of XOR gate. So if we recall, the XOR gate truth table is like this: 0 0 is 0, 0 1 is 1, 1 0 1, and 1 1 is 0. So this is, let's say, I don't know, maybe X Y, and this is maybe Z, which is the output, XOR gate output. So what we observe is, if we see these two, this one, if we observe these two and these two separately, here when X is 0, Z is following just Y, the same thing. But when X is 1, Z is becoming invert of 1. So if we think the gate as this, XOR gate, like that, and this is our X, this is our Y, this is Z here. So X can be thought of as a controller, and controller of a controlled inverter. So Y is the input of the inverter and Z is the output. So Y is, when X is 0, this is not working as an inverter, it is just a buffer. So whatever is at Y is going to Z. So when X is 0, whatever is at Y is going to Z. But when X is 1, Y is Z invert, or Z is Y invert, whatever. So it is being inverted. So here 0 is becoming 1, here 1 is becoming 0. So it can be used as a control inverter. So what we can do, we can use this information to design our circuit. So we want to, in order to subtract, what we need to do is, we want to do A. Let's say we want to find A minus B. So we want to do A plus 2's complement of B. 2's complement of B. Now, in order to find 2's complement of B, what we can do, we can find the 1's complement, then add 1. So we have to, when we want to find 1's complement, what we have to do, we have to invert each of the bits. So what we can do here is, here we have our A's here, all A inputs here, A3, A2, A1, A0 as they are, but B can become, all the B's, the 4 bits can come as a through an XOR, through 4 XOR gates, basically, each of them coming via an XOR gate. So I will draw maybe one of them because it will get clumsy. So here we have, let's say, B0, and here we have the other input of XOR, which will be all connected together. So this is B1, and finally we will have here B3, and we will of course have B2. So what's happening, the other inputs, let's draw it with a different color, maybe green. So that's one here, that's other one here, that's other one, that's other one. These four other ones will be tied together. They will be tied together, and they will be the controller. So that will decide whether we want to invert the B's here. So when this is, let's say this one is X, and when this is 0, what's happening is B3, we have B3 here, B1, B2 here, B1 here, and B0 here. So no inverting is not happening. So A plus B is, so the S will be A plus B basically. And this one we also want to connect, the X we also want to connect to C in carry in basically. So when X is 0, carry in is 0, nothing happens there, and these 4 bits are not inverted. So we have the same B here, and S will be just A plus B. But when X is equal to 1, what's happening is all these 4 are inverted. So B3 here is B bar, B3 bar, B2 bar, B1 bar, and B0 bar. This is happening when X is equal to 1. Maybe I should use a different color, I don't know, maybe just so that letters don't feel confused. So maybe so this is when X is equal to 1, so then it is getting inverted. I don't know how much sense that makes, but that's what I'm trying to say. So when X is equal to 1 instead of 0, B's are inverted here, and then also carry in is 1. So here we have all the B's are, so here we have the 1's complement, and then this C in is also being added with this one because it's being added with A and B together. So what's happening is in the end we are getting 2's complement of these this number, this 4-bit number, 4-bit binary number, when X is equal to 1, because here we are getting 1's complement, and then one more is added because the same one is connecting here, the X is equal to 1 as carry in. So here we are getting finally, not here we are getting still 1's complement, but after that this C in will be added to that as well, so we are getting 2's complement. So what we get is A plus, let's say it like that, so 1's complement of B, 1's complement, I can write it there, so 1's complement of B plus 1, that is 2's complement of B. So we are getting A plus 2's complement of B. 2's complement, I don't know, I can write that, 2's complement of B. So that is actually S minus B. So S is becoming A plus 2's complement of B. That means S is equal to A minus B. So this is how we can design this 4-bit adder to act as an adder subtractor, 4-bit adder or subtractor. So like that, adder or subtractor. So adder oblique subtractor. So like that. I don't know, it's just adder oblique subtractor. So when our X, the control input is 0, this is acting as an adder, and when this is X is equal to 1, this is acting as a subtractor, like that. So yeah.